Yeah, so I'll record. So just a quick summary, because I forgot to record. So here's a recap from last time. The magnitude is determined by the magnitude of A cross B is the magnitude of A times the magnitude of B times the sine of the angle between them. And the direction is determined by the right-hand rule, abbreviated RHR. And then here's a list of properties that I gave. A vector crossed into itself is 0 because the angle between a vector and itself is 0 and the sine of 0 is 0. Here's the properties of how the unit vectors cross. I cross j is k, j cross k is I, k cross I is j. This is the cyclic property. And you can go look at old lectures if you want more detail. And then also, the cross product is what we would call anti-commutative, which means that it does matter which order you write the cross product in. So A cross B is actually the negative of the vector B cross A, i.e. it points in the opposite direction. The last thing that I needed to cover before that I covered before I started recording was that it distributes over addition, meaning you can FOIL it out just like you can with the dot product. However, there is a caveat to that, and that's that you have to keep in mind what the order is when you're doing this distribution. And I'll give an example of how to do this sort of distribution in a moment. I just want to cover one more thing before we get there. So there is talk of this coordinate system that we use, the standard one. And so this is a very special coordinate system, right? It would not have been correct if I had decided to make x go in the other direction. That would be inconsistent with the choices that I'm making. So this is called a right-handed coordinate system, and we use those. We always explicitly use right-handed coordinate systems so that everybody agrees on, if everybody agrees on what type of, or what handedness of coordinate systems are, then we don't have to worry about someone in, I don't know, Nepal using a different coordinate system than us. As long as they use a right-handed coordinate system and we use a right-handed coordinate system, then it doesn't matter if their I or if their x points in the direction of our y, the cross products will still mean the same thing. Basically, what it boils down to is a right-handed coordinate system has the property that the unit vector in the x direction crossed with the unit vector in the y direction. If you were to use the right-hand rule to give you that cross product vector, i.e. if you use your right hand, your thumb will point in the unit vector or in the direction of the z-axis, or the vector will be the unit vector that points in the direction of the z-axis. Whereas if I had wanted a left-handed coordinate system, let's say I choose x to be this direction, y to be this direction, so I would have to use my right hand, the left hand for you guys. It would be x cross, or x cross y, and then no, I should actually, this is hard to display. So x is coming out of the page for you, so it needs to go like this, and then y is going that way for you, so it goes like this, and then z would be pointing downwards. And so that would mean that a left-handed coordinate system would be one like this. This is left-handed. And so we could have all chosen to use left-handed coordinate systems back at the dawn of time, but we didn't. Everybody chose to use right-handed coordinate systems, and so that's what we teach now, just so everybody uses the same system, because you just have to pick one. One's no more special than the other, but we need to be consistent. So if you don't use a right-handed coordinate system, then you can't use the right-hand rule. It's as simple as that. Like, they go hand in hand. No pun intended. Right, so now I said I would say something about how the cross product distributes, and it behaves almost exactly like you would expect. So let me just do a quick example. If we have A, which is AX in the I hat direction plus AY in the J hat direction, I'm only going to do two-dimensional vectors, but you can imagine that it's plus 0 in the Z or in the K hat direction. And if we have B, yeah, so the right hand would give Z pointing up, which is the consistent one. If we have B, which is BX in the I hat direction, plus BY in the J hat direction, plus 0 in the K hat direction, now we can ask what the cross product is between these two vectors. And all we're using the property that the cross product distributes over addition, and that we know what I cross j is, j cross k is, and so on and so forth. So this is equal to, and I'm just going to drop these zeros because 0 times anything is 0, so we're just going to ignore them. So we have ax I hat plus ay j hat cross bx I hat plus by j hat. All right, so I'm going to do standard FOIL, first, outer, inner, last, right? So first, I would have ax bx I hat cross I hat. All right, so all I did was I just shifted the b, or because you can always multiply a vector by a number, all I'm doing is I'm just pulling the bx outside of the vector product, just to make it a little bit more straightforward. But I could have just as easily had ax I hat cross bx I hat. That would be equally true. All I'm doing is I'm simplifying, because the cross product is associative. Right, next term, first outer. So outer is ax I hat. So outer would be these guys. So ax by, and now I have to be careful here because order matters. So this would be I hat cross j hat, because the I came before the j, right? Yeah, that would be like the left-hand rule being used on the x and y axis instead of the right-hand rule, right? All right, next term, I'm going to put these in parentheses just so it's more clear. Next term is inner, so ay and bx. So we have ay bx j hat cross I hat. Now here, the order matters, and the j came first, so I have to write it first in the cross product. And then the last term is ay by j hat cross j hat. All right, so now we can simplify, knowing what we know about about how the cross product works between unit vectors. So we already know that any unit vector crossed into itself, I hat cross I hat, sorry, any vector crossed into itself, I hat cross I hat, j hat cross j hat, is 0. So both of these terms give us 0. The only two terms that are left are these two. Now, they're not, we can't just factor, because I hat cross j hat is not the same as j hat cross I hat. Instead, we have to go check what our table says, or remember the cyclic property. We know I hat cross j hat is k hat. So we have ax by k hat. Now, j hat cross I hat is the same as I hat cross j hat, but in reversed order. And we know that when you flip the order of a cross product from our properties above, property C, you get a negative sign. So we have plus ay bx in the negative k hat direction. And so now we can simplify, and this gives us ax by minus ay bx in the k hat direction. And that is the component, or that is the component form for the vector a cross b. It points in the z direction. That shouldn't be surprising because a and b both were in the xy plane. And so the cross product of them, if your hand was rotating in the xy plane, the only direction your thumb could point is in the z direction. Now, the sign of it, whether it's up or down, depends on the relative size of ax, ay, bx, and by. But the direction, somewhere in the z direction, or the negative z direction, was already determined. Now, it's not always true that the cross product of two vectors is just in a single direction. If I had made these more complicated, if in particular, if they had had components in the z direction, if it wasn't just 0 times k hat, then this vector would have just been pointing in some arbitrary random direction. There would have been an I hat, a j hat, and a k hat component. It just would have taken a lot longer to do, so I dropped it. So I kind of just ignored it. So that's all I really want to say about vectors. Mind if I use if you use a determinant method to calculate the cross product? So later on in the course, I won't mind, but for the purposes of this homework, I would advise you to use the component form, if only because I want you to get good practice with it. Like, so this method of doing computation is more general. And I want you to get used to handling vectors in terms of components. So yes, I can go over the last two lines again. So the first and last term, ax, bx, and ay, by, both of those terms vanish because the term that they're multiplying, the I cross I and the j cross j, those vanish. A vector cross itself is 0. Now, the other property that we have is that I cross j, come on, scroll, there we go. I cross j from our properties is equal to k. So the second term, this one, we can just simplify because ax times by times I cross j is just ax times by times k hat. The third term, this term over here, is very, very close. The cross product is very, very close to the second term, but it's j cross I, not I cross j. And so from the properties of cross products that we have, that a cross b is the negative of b cross a, we can always reorder the, we can reorder a cross product as long as we pay the price of sticking in a negative sign. So j cross I is negative I cross j, and I cross j is just k, so j cross I is a negative k. And then from there, all I did is I combined like terms. So did I explicitly say that on the homework sheet? All right, so since so many of you guys already did it, use fine, but from now on, at least until we, actually, I'm gonna make one request. Go through and do at least one of the cross products using this, the unit vector notation, or the unit vector method. By the way, they give you the same answer, like they're identical. The thing about the matrix method is that it doesn't generalize well, and it doesn't explain why the cross product is what it is. So that's why I would like you guys to practice using this method, because it has more explanatory power. It helps people, it would help you intuit what a cross product really is, more so than the matrix method is. So Graham, I'm not going to answer that explicitly because that's one of the homework problems, but I'll let you think about it. What prevents you from doing an operation on two things of different units? What is it about those things that makes you not be able to, like, why can't you add together two things with different units? Whereas, and does that same reasoning stop you from doing the same thing with the cross product or the dot product? And the hint here is just try to treat units as like a variable. Anyway, so I promise that these cross products will be useful. We're not going to use them yet because we're going to talk about one-dimensional mechanics for a while, because that's a good lead up to multi-dimensional mechanics, and cross products aren't relevant for one-dimensional mechanics, but we will get there, I promise. Cross products show up a whole lot once we start talking about rotation, and it can get messy. So keep this stored away in the back of your head, and we'll get back to it in a week or 2 weeks or so. All right, so for now, we're going to change gears. We're going to move to straight line motion. Right. So as I mentioned at the beginning of the first lecture, one of the things that you must study when you're studying physics is motion, right? You have to study how things move. Now, the easiest case of motion is just motion in a single direction.
To these 5 people, should we move the train to go this way? Should we let it go that way?
Rohan, your mic is on. Right, so in the simplest case, it's just motion back and forth, or left and right. And that's the simplest because you can only consider, well, maybe it should be obvious why that's the simplest. For one, if you're worried about motion in one direction, you only have to worry about whether it's going forward or backward, or left or right. You don't have to worry about if it's moving forward or backward, and left and right. However, it also simplifies our mathematics a lot. So we know that motion, at least hopefully you know this, that motion is just the change in position over a duration, right? And so one thing that we can do is that we can use vectors to tell us, in the general case, we can use vectors to tell us relative to some agreed upon position, and maybe we say the position that we're going to call position 0, or the origin, is the UC Davis Physics Building, for example. You could tell someone using a vector where any other position is relative to that agreed upon position. It boils down to, you would go 5 miles east or 2.5 miles northwest. That's a magnitude, i.e. the distance, and a direction. So if we want to talk about change in position over a duration, that would also be a vector in the general case, because position is a vector effectively, and so a change in position would also be a vector. Now, the reason why I'm getting to this, and we'll talk about this more when we talk about multidimensional motion, is that if you are in one dimension, you don't really need to specify a direction, because it's not like there's more than one direction to choose from. You either go to the right or to the left, for example, or forward or backward. And so we can encapsulate that information just by using a sign, S-I-G-N, positive or negative, rather than an I or a J or a K. So in the case of 1D motion, vectors simplify to positive and negative numbers. The way to think about this is that, and I'm harping on this a lot because it's important. The way to think about this is that you could do all of these calculations with an I hat hanging around. Say you're worried about something moving in the on the x-axis. You could carry this around, carry this I hat 5 meters to the right in the I hat direction, or 5 meters in the I hat direction, 2 meters per second in the I hat direction. But at the end of the day, the I hat's going to factor out of every single calculation you do, just because everything is in the I hat direction. There will be an I hat attached to every single number that you write. And so because there's no ambiguity in which direction we're talking about, we can just drop that I hat. But I still want you to imagine that it's there, it's just invisible. We're just dropping it because it doesn't provide any extra information, because we already know what direction we're talking about. So what we will do in some cases is we will say something like this. Instead of saying x with a vector symbol over it, maybe as a function of time, is the coordinate position, rather, we will just say x of t is the coordinate position. And that implies that it is on the x-axis. So we don't have to have an I hat here, because we're only working along the x-axis. It's just an unnecessary window dressing at this point. All right. So now, so hopefully you guys understand why we can just drop why we don't have to work explicitly with vectors when we're talking about straight line motion in one direction, in one dimension. And that's just because it doesn't provide any useful information, the vector notation. Now we're actually going to get into what motion is, how we characterize it. So let's first talk about displacement. That's not a D. Displacement. Right, so displacement is just a change in position x of t. It tells us how much how much you've moved in one direction. So the way that we characterize this mathematically is we would write displacement. This is just the word, it's not the mathematical thing. We would call this delta x. Delta meaning change, x meaning the variable, which represents our coordinate position. And so this would be xf, final x, minus the initial x. So you would take what your final position was, subtract from it your initial position. Now remember, when I say position, this means coordinate position. So where are you on the x-axis? There's a number associated with that, so that's what it means to subtract. And if those coordinate positions are functions of time, this is really x as a or x evaluated at the final time minus x evaluated at the initial time, ti. Hopefully the subscripts kind of make sense. So when we write x, it almost delta, it almost always means final minus initial. Sometimes there are cases where we will instead use it to mean as like a positional difference, meaning, how do I want to phrase this? Actually, I don't think that, you won't see this till 9b, so I'm not going to worry about it. But generally, delta just means a difference of some sort. So there's an important note that I want to make, is that if xf, the final position on the x-axis, is smaller, i.e. further to the left on the x-axis, than xi, then the displacement is a negative number, right? And so what that means, what that negative number means, is that the final position is, say, 3 meters to the left of the initial position. Whereas if the displacement was a positive number, that would mean that the final position is however many meters to the right of the initial position. It's an important distinction. So what plays the role of direction when we're talking about one-dimensional motion is positive versus negative. That's how you know what direction the thing is moving in, or whatever process is happening. So just a quick example. Let's say, and I'll just talk you guys through this. It's written out in the notes, but I'll talk you through it. Let's say a person walks forward 14 meters, then backwards 5 meters, and then forward 3 meters, and then backwards 20 meters. What's the total displacement? So we would have forward 14 meters, back 5 meters, forward 3 meters, and back 20 meters. So the way that we would find the total displacement is you have to, well, one way that you could do it is you could think about where the person is relative to where they started. So imagine that they started at x equals 0. Well, after they walked forward 14 meters, that would mean that they're at x equals 14. Then they walk back 5 meters, so that would mean that they're at x 9 meters, because walking back 5 meters means that they are displacing their position by -5. Walking forward 3 meters would mean that they are at 12 meters, because you add 3 because it's a positive displacement. And then back 20 meters would mean that they are at -8 meters. So the initial position was at 0 meters from the origin. The final position was at -8 meters from the origin. So the total displacement is -8 meters, or equivalently, 8 meters back. Now, I just want to make a quick word of caution. There's a distinction between displacement and the distance covered. These are not the same thing. And in general, they won't be. They occasionally can be in very simple cases, but in general, they are not the same thing. So the correct answer to this question is not to just add up all of the total displacements, but the question is to figure out what the net displacement is. Now, the next thing to talk about is average velocity. So we've talked about displacement, talked about total displacement, which is just the displacement after a whole thing has happened. Let's talk about average velocity. So the question that you might want to ask is, or the question that you might seek to know the answer to if you're doing physics, is how do we describe how quickly that displacement occurred? So there's only one way to do that, and that would be to basically time it, right? If we were to time this whole event, that would tell us how quickly that displacement occurred. And the way that we quantify that in some sort of unit, some sort of measurement, is in terms of this idea called average velocity. So average velocity which I will give the abbreviation VAVE. Now, by the way, in the future, when we talk about multidimensional motion, we'll have a vector over that because this is a vector. This is just the total displacement, delta x, divided by the time it takes, right? So if velocity is going to mean what it typically does, i.e. higher velocity means takes less time to go a certain distance, then the only way to compute that is with division, right? You divide a distance by the time. And so we can rewrite what this means. Delta x is really xf minus xi, and delta t is tf minus ti. So that's what those two symbols mean. And so all we're doing is we're dividing the displacement by the duration, and that gives us an average velocity. Now, as I said, in general, since displacement is a vector, because your position is a vector, it's position measured relative to some other location, which has a magnitude and direction, you might think that this doesn't make a whole lot of sense to do, but keep in mind, you can always multiply or divide vectors by scalars, by numbers. And duration is just a scalar. It's just a number. It doesn't have a direction. So what we say then is it makes perfect sense to divide the vector displacement by a time. You just divide the components by the time, and that does give you the average velocity. So this is just to say that v average is a vector. Even in one dimension, it's a vector. We just simplify the notation by dropping the arrow, but it is a vector, just like displacement is. Now, here's another example. Let's say actually, let me write this one down. So I walk forward at 3 meters per second for 4 seconds. And then backwards at 2 meters per second for 6 seconds. The question then is what is my average velocity? So the good question, Kelsey. That's precisely what's happening here. So you might say, oh, it's just the average of 3 and 2. But that's not what's happening here. Average velocity is not just the average of the velocities that you take. It is the total displacement divided by total duration. So in this case, we travel forward for 4 seconds, going 3 meters per second. So you guys should have this intuition. This means that you would go forward 12 meters. Then you go backwards at 2 meters per second for 6 seconds. And so you'd multiply 2 by 6, and you would get 12 meters backwards. So the total displacement here is 0 meters. So it doesn't matter what the duration was. It's the average velocity is 0 meters per second because delta x was 0. It doesn't matter how long the duration is. So this is why average velocity is not just like the average of the velocities. It's just, basically, average velocity is if you take a snapshot at one point in time and then take a snapshot at another point in time, it doesn't matter what happened between it. All we want to know is what was the distance covered during that amount of time and how long did it take, and then just divide those. That's all average velocity is. So if your snapshot starts and ends at the same place, then your average velocity is 0. End of story. All right, so next thing to talk about is instantaneous velocity. And I should probably pick it up because I need to make sure I get to the instantaneous. Oh, it's actually on the next page, so I should be fine. So instantaneous velocity is similar to average velocity, but more useful. So this is the velocity during motion. So this is the quantity that you might be interested in when you're asking how fast you're going while you're on the highway. Average velocity, if you're just driving, is going to be all over the place because you're making turns and you're taking non-direct routes, but instantaneous velocity is what your speedometer reads. Well, that's actually instantaneous speed, but one-dimensionally, it's the same thing. So instantaneous velocity is at a single moment in time. So the way that we handle instantaneous velocity is we just use calculus. So we take the limit of average velocity as the duration goes to 0. That's all. And so instantaneous velocity then, instantaneous, hard word to spell. Well, maybe not. Which we don't even give a subscript, we just call it v because it's the more useful one. This is equal to the limit as delta t goes to 0 of delta x divided by delta t. Now, delta x is also going to have to go to 0 in this case, right? Because the distance that you can travel in a very, very small amount of time is going to be very, very small. And in fact, if you remember your calculus, this is just dx dt, where x is a function of time. So I'll put a little of t there. This is just the derivative of position, of your position vector. Just as a note here, notationally, so delta x is equal to x plus delta t. Sorry, that's not correct. It is x of ti plus delta t minus x of ti. So you can see why this limit would go to, why the limit of this thing as delta t goes to 0 would go to 0, because it just becomes x of ti minus x of ti. Now we can talk about acceleration too. So acceleration is the word that we use to talk about changes in velocity. This is the idea of speeding up or slowing down, right? That's what acceleration is used to discuss. And so we, just as we did for velocity, we can talk about average acceleration, which we will give little a, subscript AVE for average. This is, as expected, it is just delta V over delta T. Now this delta V here, this is the instantaneous velocity. That's important. So it's not the average of the average, it is just the average of the instantaneous velocity. And so this is VF minus VI divided by TF minus TI. Exactly as we did for the average velocity. It's just XF minus XI divided by TF minus TI. So this tells you how much does the velocity change from moment to moment. And the instantaneous acceleration is just, we give the name just regular A, which is just the limit as delta t goes to 0 of delta v over delta t, which is, just as before, it's dv dt. It's the derivative of velocity as a function of time. But v is the derivative of position as a function of time. So this is actually the second derivative of position as a function of time. And just as a word of wisdom or a word of notation, the word acceleration, that's just how, delta x is xf minus xi. So xi is the last term, that's x of ti. Xf is just delta t units of time later than ti evaluated at x. So ti plus delta t is just tf. So x of ti plus delta t is just x of tf, which is why it's just xf. And I can go into more detail of that in a minute, but I do need to finish this, so then you guys can do the homework. Right, so just as a word of wisdom, acceleration, the term as used in physics, just means any change in velocity, not just speeding up. So try to avoid using the word decelerate or slowing down. Just say it is accelerating in the negative direction, for example, which would mean the same thing as either speeding up going to the left or slowing down going to the right. All right, so last thing to cover today is equations of motion. So far, we've introduced all these ideas, displacement, velocity, acceleration, but they should fit together in some way. And so the way that they fit together So x, v, a fit together in things that are called equations of motion. Now, the specific case that we're talking about is kinematics, not kinematics, kinematics. So kinematics is going to be the name of the thing that we're about to talk about. But again, or not again, but we haven't at all talked about what causes this motion. All we're talking about is describing motion symbolically so far. So for the most part, we will deal with constant acceleration, meaning that the acceleration is in the same direction, it has the same magnitude at all times. Now, as we get further into the course, we'll generalize this and talk about less constant acceleration that's not constant, but for now, let's just deal with that. So if that's, so let's make that assumption, constant acceleration, and now let's do some math. So A is dv dt. So if that's true, how do we find out? Like, so if you were given v as a function of time, the velocity as a function of time, you could find out the acceleration by taking the derivative. But if you're just given the acceleration, how do you find out velocity? Well, we know algebraically and in calculus, you can always do the same thing to both sides. So what I'm going to do is I'm just going to integrate this equation on both sides, integrate from 0 to t of a with respect to dt prime, and that's equal to the integral from 0 to t of dv dt prime dt prime. I can always do that. And so now I'm just going to do the integral. So the left-hand side is a of t minus, or a times t minus a times 0, so it's just a times t. And this is equal to, well, this is the this is the fundamental theorem of calculus. The integral of the derivative is just the function. So this is v at t minus v at 0. And so rearranging, we get v as a function of time is equal to at plus v at 0. And we're going to give this thing, v at 0, we're going to give it the name v naught. So the equation that you'll see everywhere is v of t is a of t, or a times t, plus v naught. V naught is just the velocity at time 0. And so we can do the same thing with position. We know that v, velocity, is the derivative of position, of the coordinate position x. So let's integrate both sides again. 0 to t of v of t prime dt prime equals 0 to t of dx dt prime dt prime. So now, but we already know what v of t is, so we can plug that in and do the integral. So we are left with 1/2 a times t squared plus v naught times t. And then there would be a term that would be like all of that stuff times 0, but it's 0, so it's just 0. And this gives us x of t, again, by the fundamental theorem of calculus, minus x of 0. And again, we're going to call this x of 0, we're going to call it x naught, the position at time x equals 0. So together, for constant acceleration A, so this is only valid for constant acceleration, by the way. The process is correct, but it'd have to generalize more, because if the acceleration wasn't constant, then this would be some function that you'd have to integrate, right? So for constant acceleration A, we get the equations v of t equals a times t plus v naught, and x of t equals 1/2 at squared plus v naught t plus x naught. And these are our kinematic equations. Now, you can combine these in any which way you want. But the important point is that these are the fundamental kinematic equations that describe one-dimensional motion for constant acceleration. And then you can rearrange them and make new things if you want to. So let's talk about the terms that are present here. So there are a whole bunch of symbols. There's a, t, v naught, x naught, and so on. So let's label those. So t is the independent variable. X of t and v of t, those are our dependent variables. And then finally, everything else, it's a constant. X naught, v naught, a, they're all constants of motion. So if you know those three constants, then you know how the thing moves, assuming it's constant acceleration. The point, that last bit is that we assumed that a is constant. It doesn't have to be, but for the case that we're worried about right now, we are assuming that a is a constant. So if you can characterize a, then you can and x naught and v naught, then you can characterize the entire motion. Now the last thing, or second to last thing I talked about, we might have to go like 2 or 3 minutes over. You should know how to derive them, but that takes some time to think about. We can always rearrange. I was really hoping to get to the next thing. We can always rearrange these equations to get other equations. That's just true. Just by naming things and thinking about what they mean. So for example, the equation 2a times xf minus xi is equal to vf squared minus vi squared. This is just a true equation. It's a consequence of those two. So if you plugged in that xf is x of tf, and xi is x of ti, and vf is v of tf, and vi is v of ti, you would find that after doing some substitution for what x and v are, you would find that this equation is true. However, by writing it this way, we've eliminated the variable t from these two equations, which you can always do, right? You can eliminate variables from a pair of equations. And there are other combinations that you can make that can let you express other things. But I'll leave those to you guys to work out or to read about, because makes you do some critical thinking. All right, last thing to talk about, what you need for the homework, so do stick around, is free fall. So just as a quick moment, let me share a different screen, which is something neat that happened more than 50 years ago, 51 years ago. Can everybody see this? Is it sharing? Okay. Hammer, feather.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Right, so what that was just a demonstration of the fact that I'm about to tell you. Free fall on the surface of a body is constant acceleration downwards. That's how downwards is defined, by the way. It's the direction that free fall happens in a straight line. So on Earth, the acceleration rate, we call that almost done, I promise. We call that acceleration rate g. We just abbreviated g, like pi means 3.1415, blah, 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 blah. The amount of acceleration on Earth is just called the letter g. And it's about, that's not how you spell about. it is about 10 meters per second squared downward. Of course. So g, the vector, is, the magnitude of that vector is 10 meters per second squared. And so for this course, don't use 9.81. It'll make my life harder, it'll make your life harder. Just use 10. And it's within 2%. Or if you're really tricky, you can use pi squared. It's about pi squared meters per second squared as well, if you really want to get cheeky. But don't use 9.81. Right, so use 10 when you're talking about g. So the point is g is a vector that points downwards. But in one-dimensional motion, when you choose a coordinate axis, you can choose that up is positive, so then down would be negative. So the acceleration vector would be downwards, or would be negative 10 if you choose up to be positive, if your coordinate choice is up is positive. No, you can use 9.8, just please don't in the future. It'll just make me sad if you do. All right, so I guess that's as far as we're gonna get today, not as far as I would have liked.